Okay, so for this last and final lecture from me, we're going to be talking about peripheral hemodynamics and the introduction to pulmonary physiology, and get a little bit into respiratory stuff at the end of this lecture. Okay, so let's talk a little bit about something which is called hydrostatic columns. Hydrostatic columns are represented by the length of our blood vessels in humans. The pressure at the bottom of the hydrostatic column is greater than the pressure at the top of the hydrostatic column, because the pressure is determined by the length of that fluid. Right here. So here we have our diagram here. These are actually a real human of all blood vessels preserved, which is pretty neat. All right, so let's move on to barometric pressure. Why is barometric pressure higher at sea level than when it is at 10,000 meters up in the air? Because a length of a column of air is longer at sea level than the length of a column of air at 10,000 meters. That column is 10,000 meters longer. So at sea level, pressure is about 760 millimeters of mercury. What happens to barometric pressure as we go up or as we ascend into altitude? The pressure goes down because the length of a column of air becomes then shorter, so then it exerts less pressure. Okay, so this is an important concept with regards to humans, okay? So now let's relate this back to humans. We talked about a length of column of air and the barometric pressure at sea level, and if we descend into altitude, why is it different, right? Because ultimately that column of air is shorter as we ascend. So the pressure it exerts on all the molecules is going to be less. Okay, so when a person stands up, their hydrostatic columns are as long as they possibly can be. So when you're in the upright standing position, if you change your posture, you will change the length of those columns because the columns are influenced by gravity. If you go from an upright standing posture to a supine posture, the effect of gravity on the hydrostatic columns is now minimal, because those hydrostatic columns are now running parallel. They're not vertical. So if we are seated, they are somewhat in the middle, somewhat vertical, somewhat horizontal, so they'll be kind of somewhat in the middle. Okay, so you see right here when someone is standing in the upright posture here, the length of our blood vessels are as long as they're going to be, right? And what are we working against? We're working against gravity. And that's an important concept to know. Okay, so let's talk about our hydrostatic columns, which are pretty much our blood vessels, and related to cardiac output. So on average, cardiac output averages about 5 liters or 5,000 milliliters per minute. This is dependent upon the amount of cycles per minute and how much blood is going to be ejected per cycle, right? So heart rate times stroke volume is our cardiac output. That's important. So the number of cycles per minute is heart rate. Stroke volume, again, remember, is that volume of blood ejected with each systole. Okay, let's talk about gravity and venous return. When a person is standing and the hydrostatic columns are long, gravity is impacting negatively on the ability for you to maintain venous return, because gravity wants to pull all that fluid down towards the feet, right? So we're constantly working against gravity, and gravity wants to pull all of our blood and pool at all of our feet. So that's something that is working against us constantly. Okay, but fortunately, there are venous valves that shut after the blood passes through and can keep the blood moving up and back to the heart. So in a standing position, because this is good in a standing position because postural muscles are at work. These are considered our anti-gravity muscles. This keeps you in the upright position. So the muscles are compressing some vessels and help move blood back up. So taking all of the hydrostatic columns into consideration, it is safe to say that venous return and end diastolic volume is lower in that posture than in any other posture. So heart rate will most likely be higher in order to maintain the cardiac output of 5 liters. Right, so last we talked about that skeletal muscle pump, right? So it squeezes on these vessels, which also helps aid in venous return back to the heart. That's what this is representing here too. And this is where we have a closed valve. So if we zoom in here, we're on the venous side of circulation. So we're returning blood back to the heart, right? So this is our venous valve opened. It's allowing blood to come up going back up to the heart, and then boom, we shut it and the muscle compresses, so we keep squeezing the blood back up, back to the heart in order for us to maintain a solid venous return. Okay, so let's continue with this posture and cardiac output and how that affects it. When we're laying down here, when we're parallel again, right, we aren't working against gravity at this moment. So we eliminate the negative impact of those hydrostatic columns. So no gravity is working against our venous return, or it's the path of least resistance when we're laying down flat parallel on our back. Okay, so now venous return can be as large as it possibly could be, so that obviously will impact upon stroke volume as well. So we still maintain our cardiac output of 5 liters per minute. If we enhance venous return, end diastolic volume will increase, and therefore stroke volume will increase, right? So then that means heart rate can come back down, because cardiac output is heart rate times stroke volume. So if we're increasing end diastolic volume and stroke volume, that means one of the variables can come back down, and we're still maintaining that cardiac output. Now when we switch and we're here and we're standing, now gravity is impacting negatively upon these vessels here. And it really wants it to pull it all to our feet, so we have to work harder for those venous valves to shut, our muscles to contract, so we can have a nice venous return to the heart up here. Now that means we are going to have a lessened venous return in an upright standing posture as compared to laying down. So that means if we have a lessened venous return, we'll have a lessened end diastolic volume, and therefore a slightly lessened stroke volume. So what variable has to increase in order for us to maintain that cardiac output of 5 liters per minute? Heart rate would then have to increase. So you would see that your heart rate standing is actually going to be higher than if you were to lay down. So if we were to do an experiment in class and I had all of you lay flat on your backs, I'd rest for about 2 to 3 minutes and measure your heart rate. We would measure your heart rate and so forth. And then I would have you go in the seated position and then the standing position. But if we compared the laying down parallel position compared to when you were standing, your heart rate will be higher in the standing position than when it is laying down. That's because your enhanced venous return laying down and enhanced stroke volume, you're allowing heart rate to come back down. That makes sense when you sleep, that your heart rate is also much lower when you sleep. So when you look over here at this diagram, this is represents somewhat in the middle, right? So everything is somewhere in the middle. Venous return will decrease a bit and heart rate will increase a bit when you go from laying down to a seated posture. So this means when we exercise, this is very important, posture needs to be taken into consideration. So impact of what the exercise is going to be from a heart rate or stroke volume perspective is going to be influenced in the posture in which the exercise is done. So that's very important. If anyone ever performs some sort of exercise testing or any baseline data, always get baseline data in the position that the person is going to be exercising in. Because if I took heart rate and then, hooked them up to a couple machines and measured heart rate and stroke volume with them laying on their back, but then they were going to be exercising in the standing upright posture, how do we know how much heart rate has increased due to the exercise modality, or is it because just naturally your heart rate's going to increase due to the negative impact on gravity? So always get baseline data in the position that the person will be exercising. So if you're having someone in a seated position on a bike, make sure you get baseline data in a seated position on the bike, because that's going to give you your most accurate baseline data. And then you can attribute more of your results to your exercise modality as compared to posture. And if, say, someone, you're going to exercise someone down laying on their back and you took their resting data from them standing up, that's going to affect it. So again, just make sure you always take posture into consideration. Okay, let's talk about vasomotion. So allowing all of these blood changes to occur in vessels and decrease and increase in stroke volume and all of that, and into blood shunting to one area from the other, all is determined by something called vasomotion. What is vasomotion? It's the ability to change the size of our blood vessels. So this is critical in changing pulsatile flow to steady flow. Right, so when we exercise, there are 2 limiting factors that limit your ability to continue to exercise. 1, any change in temperature. 2, any change in pH. So again, remember, exercise is a planned deviation from homeostasis. As humans, we are physiologically want to remain in a state of homeostasis because this is where the state our cells like to function, right? So let's go back to one of our first couple lectures of bioenergetics. We like to maintain homeostasis because our cells like to function there. So no matter what we do, what type of stress we put on our body, our body's going to constantly try to get us back down to that area which we like to function. So when we exercise, we force a deviation out of that homeostatic state, and then we affect temperature and pH. We affect both of those when we exercise. Okay, let's talk about exercise and what adjustments we need to make. So when we exercise, we need to make neural adjustments. We talked about this last time, right? We turn off the vagus nerve and our heart will automatically return to its intrinsic rate of 100 cycles per minute, right? What does the intrinsic rate mean again? That means if we were to remove all neural and hormonal or endocrine factors influencing heart rate, it would completely go to its own intrinsic rate of 100 cycles per minute. All right, so after that, we will kick on the accelerators, right? Our sympathetic nervous system in order to increase our heart rate higher than 100 cycles per minute. So why do we need to circulate blood faster? One is the delivery of oxygen and nutrients to the working cells. Two, always the removal of waste. So then what causes those cells to compromise function? A change in temperature or pH, right? So as metabolic rate goes up, you've got more heat. The more work you ask your cells to do, the more waste you have, and we need to get rid of this waste because this will cause pH to drop. Okay, so blood is our best transport medium we have for transporting heat. Our faces get red when we exercise because we are bringing blood to the surface. We want to get rid of that heat since it is a component that is compromising cell function and the environment, right? Major threats to homeostasis, change in pH, change in temperature. And when we exercise, we're changing both. So we have waste, which is collecting. So we have carbon dioxide, we have hydrogen ions, we have free-floating calcium, potassium, magnesium, chloride, all of that good stuff, etc. All of this can compromise cell function and the environment, right? What we're going to worry about a buildup of hydrogen ions is what's going to affect what's going to affect pH. Right? But we are making this decision by choosing to exercise. But the more we do it, the better we get at it, right? So the better we get at tolerating waste products and we will start to remove them more effectively. So now we can exercise at a higher intensity and not suffer negative effects as much. So the more frequently we do this, the better our cells adapt in removing waste efficiently and being in that uncomfortable environment. So ultimately, what do we call this? We call this fitness. So ultimately, when we train someone, you want them to get better at deviations from homeostasis. So anytime you train anyone, you ultimately are trying to get them to be better at deviating from homeostasis. That's pretty much what we call fitness. Okay, so in the next screencast video, we're going to start talking about blood flow and different shunting capabilities to different body parts and what happens during exercise.